Hello and welcome to the CNN workshop, which is conducted by Dilpreet Bar and myself, Mohit Bakshandani. So you might be wondering why you're looking at a picture of a bird right now. Um, let's actually think about how we identified this creature to actually be a bird. Maybe it was the beak or the eyes, maybe it was the head of the bird, maybe the structure, maybe the claws. There's some feature that's probably telling us that what we see right now is a bird. Now, let's say that, let's say what happened. Okay, so let's consider another image, this one. Yeah, and let's think about how a computer would process it. That's actually why we use convolutional neural networks, and that's actually why they were discovered. So there's some patterns that exist within an image, as we just discussed. There's birds. For birds, there's beaks, there's eyes, their head structure, the body structure, wings, claws. Right? Let's look at the beak. Um, yeah. Okay. So the beak right here has some unique features which the computer could identify, and it could tell us that that part right there, that's a beak. So essentially what we have in our hands is a beak detector. Pretty cool. Now let's look at different patterns, or rather different birds, but with similar sort of structures, because we know that all birds have beaks, right? So let's look at these two birds. The first one is what we looked at earlier. So in that image specifically, the beak is located on the top left corner, right? So our computer does some process. We'll understand what that process is, and it tells us that the beak is located in the upper left corner. Now, for this bird, we know that the beak is located on the center of the image, almost the center of the image, right? So it will carry out some processes and tell us that, okay, this beak is located on the center of the image, right? So essentially what both of these operations are doing is going through every individual pixel that exists. Let me draw this out. Okay, 1 second. Great. So it's essentially going through every pixel, right? And it's locating where the beak might actually be. And in this case, it's right here. Okay. So, well, we have some sort of correlation here. And correlation itself is locating the beak, right? So now let's dive deeper into what a convolutional neural network is. So a CNN is a neural network with some convolutional layers and some other layers. A convolutional layer has a number of filters that does a convolutional operation. So let's look at this diagram here for a second. We have an input image, which was probably our bird. This is a filter, right? Which was our beak detector, essentially was a filter, right? We're looking for the beak, which finds the beak and compresses it into a smaller output image, right? Which locates the beak and tells us that what we're looking at is the beak. Okay, let's look at what a convolutional operation is, or what a convolution is. Let's say you have a 6x6 image, right? Which is converted into um, binary numbers, 0 indicating a white pixel and number 1 indicating a black pixel, right? So let's say you have this 6x6 image, which is like a matrix, and you have these two filters. Now, if you notice, there's actually a pattern that's being detected, right? Or there's a pattern that we can detect. You can see that right here. That's our first pattern that we're trying to detect, and this is the second pattern that we're trying to detect, right? So in this one, it's +1 going diagonally, and in this one, it's +1 going vertically. So let's actually look at what happens with these filters, right? Before that, um, these filters they're actually not programmed by us. The the neural network essentially learns or creates these filters automatically using various backpropagation techniques, which we won't get into today. But yeah, so let's look at if what happens if we have this 3 by 3 matrix and we compute the dot product of this 3 by 3 matrix when it's over on essentially on top of it, right? So let's try to compute the dot product of this. This would be 1 into 1, which is 1, plus 0 plus 0, because that's 1 into 0, that's 1 into 0, that's 1 into 1, so that's plus 1, and that's 1 into 0 again. This is 0 into 0, 0 into minus 1, which is 0, 0 into minus 1 again, so that's 0, and then we have 1 into 1, which is plus 1. So the dot product of this is equal to 3. Now let's verify whether that's correct. And yeah, that is correct. Now, what we do next is take a stride. So a stride is equal to 1, which is basically the number of rows we would skip to move on to our next convolution operation, or to our next convolution operation on this image, right? So as you can see, it moves one column away. So what we get is this, and now we have a filter over this 3 by 3 3 by 3 array. Now we can compute the dot product of this filter on top of this 3 by 3 matrix, and what we essentially get is -1. Now let's look at what happens if our stride is equal to 2. Well, we know that the dot product of this 3 by 3 matrix of this filter is 3. And if we take a stride of 2, it moves 2 columns from its initial position. And now we compute the dot product of this filter with this 3 by 3 matrix to get -3. Great. Now let's just complete what we started initially, where we had this filter, this 3 by 3 filter, and what we're essentially doing is computing the dot product of this 3 by 3 filter with this 3 by 3 array with stride is equal to 1. So when we do that, we get 3, move 1, we get -1, move 1 more, you get -3, and so on and so forth. Okay, great. And then finally, this last one, we get -1. So as you can see, as I previously mentioned, there's a pattern that's here, and that's a positive one diagonal pattern going from top left to top, or top left to bottom right, right? So we know that this pattern exists right here and right here, right? And so this computer. The computer can find out these patterns of numbers, and let's look at what their dot product values are. Well, both of them have the value of 3, which means that both of these are similar in some way, right? Now, let's look at what happens when we have filter 2 and we compute the dot product of, well, filter 2 with this 6 by 6 image. And essentially, we repeat that for every filter. In our example, we only have 2 filters, so let's see what happens. And computing the dot product, finally we get 3. Now, essentially what we have here, once we have filtered our image, is a feature map. So what a feature map is a 2 by 4 by 4 matrix. It's a 2-dimensional array, essentially, and you have a 4 by 4 matrix. And this essentially forms 2 images with the 4 by 4 dimension. Now let's look at what happens when we have a colored image. We know that any colored image is essentially can be broken down into its 3 components of colors, which is red, blue, and green, right? So that's what happening here. We have this weird little dog broken down into its primary colors. And what we have essentially is the same thing as we had earlier, but it's just 3 dimensions because we have 3 colors. And for our filters, we have a three-dimensional filter instead of a one-dimensional filter. Okay, so this is what actually happens in CNN. You have your image, you you perform a convolutional operation on it, and then a max pooling operation, and then you can essentially repeat this process multiple times and then flatten the data later on. Let's look at what max pooling is. So as we saw that this was the dot product from our first filter, and this is the dot product from our second filter. Let's break this dot product, or this feature map of the first filter, and let's break it down into 4 2x2 arrays, or 2x2 matrices, whatever. What we get by performing the max pooling there is essentially it would calculate the maximum value from this. So we know the maximum value from this would be 3, from this it would be 0, from this it would be 1, and from this it would be 3, right? And what we essentially do is get a smaller image from that. Let's look at it again over here. Yep. Where all of these values are equal, so let's just take out this -1. Over here would be 0, 3, and 1. Let's check if that's correct. And yeah. So let's look at why we undergo or why we perform pooling. Let's say that this is the image of our bird, and we undergo subsampling, which is essentially just pooling data, right? And what it does is make the image smaller, right? And therefore we can add fewer parameters to characterize our image. Now we've looked at convolutional layers, convolutional operations, my bad, and the max pooling layer to form a 2x2 image, because so we know we have 4 values here and we have 4 values here. You have these on top of each other, so that's a 2x2 image, right? Now if you remember, initially we started by with a 6x6 image, and now it's broken down into a 2x2 image. Right? Okay, let's look at why we can't sort of perform the same operations with a artificial neural network, or rather with a fully connected layer, and why we should use convolutional layers or convolution. Let's say if I have a 6x6 pixel, 6x6 image, we know that would have 36 pixels. Well, that is relatively small, but let's make it bigger, because we know that an image won't have 6x6 pixels, right? That's realistically not possible. Let's look at something bigger. Let's say you have a picture of size 1920 by 1080. That's probably your screen size right now. Yeah. That would have a lot more pixels. And essentially, that would be a lot more weights for us to calculate, for the computer to calculate. And that's a lot for the computer to take. Therefore, convolutional operation is much better. Convolutional layer is much better. So the benefits of a CNN. Okay. So we performed a convolutional operation and a max pooling operations to get a new image. And we know that the image size is smaller than what we initially started off with. And the number of channels is the number of filters, which is what we also saw in our RGB example. Okay, so essentially after every convolution and after every max pooling layer, what we have is a new image, right? And this new image is essentially as we saw, a 2x2x2 matrix, which is then flattened. But there's a very essential point which is missing here, and that is the activation function. Now, there's many activation functions that exist, but the most common one is the ReLU activation function, in CNNs at least, and that essentially converts all negative values to zeros, and all positive values remain. But we won't be going to more detail to that today. Let's look at flattening. Well, essentially, earlier we had this 2 by 2 by 2 matrix, which when flattened is this. You have a 1 by 3, 4, 5, 6, 7, 8. You have a 1 by 8 matrix. And this is then connected to a fully, this is then um, connected into a feed forward network. And that's pretty much it.